Okay, from the textbook, here we have our Ka expression that we discussed in the last video. Ka equals the concentration of H3O plus times concentration of A minus divided by the concentration of HA. Note that H3O plus and H plus mean the same thing. Either you're going to write your equation as Bronsted and Lowry would, or you'd write it as Arrhenius would. Either way, you get the same result. It's also in your book a table of various Ka values, and you're not going to have to memorize any of these or anything like that, but something to note that when you look at these various acids and you look at the Ka values, note you got a couple 1 times 10 minus second here, but then we go 4 times 10 to the minus fourth, 6 times 10 minus fourth, 6 times 10 to the minus fifth, times 10 minus fifth, 2.9 times 10 to the minus eighth, times 10 to the minus 10th. What we're finding is for weak acids, most of the time the Ka value is going to be smaller than 10 to the minus fourth, which means, as we're about to find out when we're going to determine the concentration of H plus in the solution, we're going to have to use ice tables since these are weak acids and everything's in equilibrium. And because the Ka values are so small, we will routinely be using the shortcut that we learned in the previous chapter. Okay, so let's move on now to the autoionization of water. Sounds impressive. It's, not really. Here's the deal. Note, yes, here's the table that we looked at. Ka is usually much less than 1. So what that also means is at equilibrium, you in general have much more Ha, much more of the acid containing the proton than H plus. All right. So, autoionization of water. Essentially, as Arrhenius would write it, H plus liquid is in equilibrium with H2O liquid, is in equilibrium with H plus aqueous plus OH minus. Liquid water dissociates into H plus and OH minus. Now, if you are going to write the equilibrium constant expression, products over reactants, notice our reactant is a liquid, so this is just the equilibrium constant expression. Since it's water, we're going to call it Kw, equals the concentration of H plus times the concentration of OH minus. Now, the question is, what are these concentrations? What is Kw? It turns out Kw has been measured, has a value of 1.0 times 10 to the minus 14, which tells us that this equilibrium reaction here, the equilibrium constant is Kw, it's 1 times 10 to the minus 14th, which means at equilibrium we have very, very little H plus or OH minus in an aqueous solution. It's mainly just water. So water, pure water, consists of mainly H2O molecules, non-dissociated. Just a tiny bit dissociate with a Kw of 1 times 10 to the minus 14th. However, we can calculate the amount that did dissociate with an ice table. Because here's the reaction. This is how Arrhenius would write it. Bronsted-Lowry would be H2O plus H2O in equilibrium with H3O plus and OH minus. They'd get the same Kw expression because we know H3O plus and H plus are the same. But doing the ice table, what we find is, okay, ice table, H2O in equilibrium with H plus OH minus. Since our H2O is a liquid, it will not appear in the equilibrium constant expression, so I'm just going to put little dashes here to indicate we don't care about any of that. Initial concentration of H plus is 0, OH minus is 0, plus X. At equilibrium, we have X and X, which means plugging X and X into our values of H plus and OH minus, and plugging 1.0 times 10 to the minus 14th in for Kw, that means 1.0 times 10 to the minus 14th equals x squared. X equals 1.0 times 10 to the minus 7th, which means in pure water in a neutral solution, the concentration of H plus is 1.0 times 10 to the minus 7th molar. The concentration of OH minus is 1.0 times 10 to the 7th molar. It turns out in any aqueous solution, in any solution where the where the solvent is water, this holds that the concentration of H plus times the concentration of OH minus equals 1.0 times 10 to the minus 14th, our value for Kw. This Kw holds up in any aqueous solution. What that means then is if you add something into your solution, such as an acid makes the concentration of H plus go up. Well, if the concentration of H plus goes up, then the concentration of OH minus must go down, because the concentration of H plus times the concentration of OH minus must be 1.0 times 10 to the minus 14th, no matter if it's acidic, basic, no matter what. So if you add an acid, that means you've added a proton donor. The concentration of H plus goes up. The concentration of OH minus must go down, must become smaller to maintain this equilibrium constant, this Kw. If the concentration of H plus is larger than the concentration of OH minus, we call the solution acidic. Concentration of H plus is less than the concentration of OH minus. We have more hydroxide than protons. It's basic. And if the two equal each other, 1 times 10 to the minus 7th molar, we call that a neutral solution. So we can do some math with this then. Yay, gotta love math. If the concentration of H plus is 1.0 times 10 to the minus 7, if the concentration of H plus is 1 times 10 to the minus 3rd molar, what is the concentration of OH minus? Well, Kw is concentration of H plus times concentration of OH minus. Kw is 1 times 10 to the minus 14th. We said our concentration of H plus was 1.0 times 10 to the minus 3rd. So then, just spelling this out real longhand, concentration of OH minus is our Kw divided by that concentration of H plus. It's 1.0 times 10 to the minus 11th. And you got to put in our units because we're dealing with concentration. This is 1.0 times 10 to the 11th molar. That is the concentration of OH minus here. Alrighty, well, let's do some more math. And yes, hopefully you're finding this math is not too difficult. What if the concentration of OH minus is 9.2 times 10 to the 11th molar? What's the concentration of H plus? Same thing, you plug it in, and you find the concentration of H plus is 1.1 times 10 to the minus 4th. Yes, that is right. Molar, since it's concentration. All right, and then people, including myself, get tired of saying 1 times 10 to the minus this molar, 1 times 10 to the minus 11th, 1 times 10 to the minus 6th. It just gets annoying. And so we came up with the pH scale. pH is the negative log of the concentration of H plus. And what this does is it takes things like 10 to the minus 11 and makes it 11. The pH scale goes from, well, the book says 0 through 7 to 14. 7 is neutral. Concentration of H plus equals the concentration of OH minus. That's at pH 7. It's neutral solution. Any pH lower than 7 is acidic. Any pH larger than 7 is basic. Most books have it go from 0 to 14, but there are example problems where you can get pHs of 15, very, very basic solutions, and pH, well, what's less than 0? Yes, you can have pHs of -1. It's actually quite easy to make a -1 pH solution. All right. So, although most books have 0 to 14 as a scale, it's really more like -1, almost -2, to like 15.5, maybe 16. All right, but if you're at less than 0, if you're in negative pHs or greater than 14, you are way in the extremes. Extremely, extremely basic solutions or extremely, extremely acidic solutions. All right, so we can do some math. If the concentration of H plus is 1.0 times 10 to the minus 3rd molar, what's the pH going to equal? Well, pH is negative log 1 times 10 to the minus 13th, or 1.0 times 10 to the minus 3rd. And then, yeah, this is just math. This is just calculator. Make sure you can put this in your calculator correctly. pH is 3.00. Now we have to look at some sig figs here, because if we look at this, if I said, okay, the H plus concentration is 1.0 times 10 to the minus 3rd molar, how many sig figs does this number have? Rightly, you would say, well, it has 2 sig figs, because the 1.0 is a sig figs, times 10 to the minus 3rd, that does not get included in the sig figs. That's just telling you where the decimal is. 1.0 is the 2 sig figs. It turns out when you take the log, and get this pH, this 3 comes from the 10 to the minus third. Therefore, this 3 does not count in the sig figs. Only the digits after the decimal place count as significant figures. This 1.0, when doing the log function, gets translated into the 0, 0. The times 10 to the negative third becomes this 3. So this 3 is not part of the significant figures since it comes from the negative third. Oh, I've got it right here. 10 to the negative third gives us the 3. The 1.0 gives us the numbers after the decimal place. So if you're saying what's the pH of the solution and you're worried about sig figs, however many sig figs you have here, that's how many digits after the decimal place you have in the pH. All right, so more example problems here. If the OH minus concentration is 1.0 times 10 to the minus second molar, what's the pH? Well, pH is negative log of H plus. If this is the OH concentration, I'm going to need the H plus concentration. Good news, as long as I have OH, I can calculate H plus, because concentration of OH minus times concentration of H plus equals Kw. The math we just did, we can calculate the concentration of H plus from the 1.0 times 10 to the minus second molar OH minus, and then we can plug that into the log equation, and note 1.0 times 10 to the minus 12th. This 10 to the minus 12 becomes the 12 here, and the 1.0 is 2 sig figs, and that's a 0, 0. And I don't want to mislead you here. We've been looking at, oh, this is easy. Whatever this number is comes down here. No, that's actually not quite the case. That's not actually how it works. All right. It just so happens if this is 1.0 times 10 to the something, then whatever that something is actually comes down here. That's just the way logs work. But if this number here for our concentration of H plus is not 1.0, you really have to put it in a calculator to get the right answer. Unless you're an old school chemist and can pull out your slide rule. Okay, concentration of OH minus is 2.7 times 10 to the minus fourth molar. What's the pH? Well, concentration of OH minus, we need to get the concentration of H plus, so we plug it into the Kw equals H plus concentration times OH minus concentration. We find the concentration of H plus is 3.7 times 10 to the minus 11th molar. So then the pH is a negative log of 3.7 times 10 to the minus 11th. pH equals 10.43. Note, when you don't have a 1.0 here, you can't just take the 4 down and put it here. You can't just take this 11 down and put it here. Okay? You have to put in the calculator, do the math, pH 10.43. But note, the concentration of OH minus is greater than 7, or 1.0 times 10 to the minus 7th molar. Concentration of H plus is less than 1.0 times 10 to the minus 7th molar. Therefore, we'd expect this to be a basic solution with a pH greater than 7, and it is. pH is 10.3. Okay. It turns out there can be a slightly easier way to do these problems because, recall, pH is the negative log of the concentration of H plus. There's another term, pOH, is a negative log of the concentration of OH minus. And with a little math, a little derivation, we find that the pH plus the pOH must equal 14. It's just, when you do math with logarithms, remember the rules of logarithms from algebra class, when you can just take the Kw equals concentration of H plus times the concentration of OH minus, take the negative log of both sides, and this is what you get. So that makes it easier. Let's look at our previous problem. Concentration of H plus is, concentration of OH minus is 2.7 times 10 to the minus fourth molar. What's the pH? The old way we did it was change this into the concentration of H plus and then take the pH. We could just take the pOH. The pOH is a negative log of the concentration of OH minus, Negative log 2.7 times 10 to the minus fourth. The pOH is 3.57. Then we know, okay, 3.57 our pOH plus whatever our pH is must equal 14. So then 14 minus 3.57 is the pH, and that's 10.43, which is the same answer we got previously when we did it the other way by first changing OH minus concentration into H plus concentration, then taking the pH. You can do it either way, whichever way you find is easier for you. For me, the easiest way is whatever requires me not to re-enter stuff on my calculator. Often, if you've got an OH concentration, the easiest way to not enter stuff on your calculator is to just take the pOH and then subtract that number from 14 to get the pH. All right. I know what you're thinking now. This is fun, but hey, where did the ice tables go? We'll start doing ice tables in the next video.